This is a 2D FDTD simulation region with one unit cell of a grading structure in the simulation region. Block boundary conditions are set at the x-min and x-max boundaries of the simulation region since the structure is periodic, and the plane wave that will be added will be injecting light at a non-normal incident angle. PML boundaries are used above and below the structure in the y direction to absorb transmitted and reflected light from the structure. A frequency domain profile monitor is used to measure the fields over space in the xy plane, and a linear power monitor is placed near the y-max boundary of the simulation region to measure the reflected fields. To set up the plane wave source incident on the grading structure from the air above the structure, start by adding the plane wave source from the Sources menu in the main toolbar. Click on the Edit button or use the E keyboard shortcut to open the Source Edit window. In the last unit, we went over the 3 available plane wave types: block periodic, B-fast, and diffracting. Remember that the block periodic type is recommended for simulating an infinitely wide plane wave source for the plane wave injected at normal incidence, or single frequency simulations where the source is injected at angled incidence. If the broadband response for an angled source is required, then choose the B-fast plane wave type. Here we'll choose the block periodic plane wave type. Set the injection axis to y-axis and the direction to backward to inject a source propagating towards the negative y direction. Set the angle theta to 15 degrees and leave angle phi at 0 degrees to inject at 15 degrees from normal relative to the xy plane. Set the polarization angle to 90 degrees to rotate the direction of electric field polarization from the x direction to the z direction. Next, in the Geometry tab, set the x-span of the source to 5 microns, which is wide enough to span the entire x-span of the simulation region. Set the y position to 2 microns, so that the source is injected from the air above the structure. The z position and span will not be used since the simulation region is 2D, which means it will be as though the structure and source are uniform and infinite in the z dimension. Next, in the Frequency Wavelength tab, set the start and stop wavelength both to 0.8 microns, which is the wavelength of interest. Check the Beam Options tab, which shows a plot of the injected angle of the plane wave over wavelength. Since we have a single frequency source, there's only one point on this plot. However, if you were injecting a broadband source at an angle, you would see that the angle will vary over wavelength when using the block periodic plane wave type. The B-fast source type can be used to get a constant angle of injection over wavelength. Now click OK to accept the settings. Check the CAD viewports to make sure that the orientation of the electric fields is in the Z direction, indicated by the blue arrow, and the injection direction, indicated by the pink arrow, is angled as expected. I can also make sure that the gray shaded injection region is not overlapping with the reflection monitor or intersecting with the grading structure. You can also run the simulation to confirm that the source is injecting the expected plane wave. Right-click on the structure group and disable the grading structure temporarily, and run the simulation to simulate the propagation of the plane wave in free space. After the simulation has completed, right-click on the profile monitor and visualize the E result to plot the electric field profile. By default, the plot shows the magnitude of the electric fields over space, so you can see that the fields have an amplitude of 1 in front of the source and 0 behind the source, since there's no reflection. Under the Vector Operation column, choose the field component to plot. Since the source is EZ polarized, the EX and EY field components are 0, and the EZ field component shows the angled phased fronts of the plane wave as expected. Next, right-click on the profile monitor and visualize the P result, which is the pointing vector. The direction of the pointing vector shows the direction of power flow. Select the vector plot type. Here you can see arrows in the vector plot showing the angle direction of power flow. The amplitude of the pointing vector is indicated by the color scale shown on the right. Now switch back to layout mode by clicking the layout button and re-enable the structure group and rerun the simulation. After the simulation has been run, right-click on the monitor above the source and plot the t result, which gives the fraction of injected power which gets reflected by the structure at a wavelength of 0.8 microns. Let's review some points to remember about plane wave source types and boundary conditions. If simulating a block periodic plane wave type, always use periodic or block boundary conditions at the sides of the simulation region in the periodic direction. If PML or metal boundaries are used at the sides, there will be edge effects. When using the BFAST type plane wave, BFAST boundaries will automatically be used in the directions of periodicity, overriding any other boundary condition settings in these directions. When using the block periodic or BFAST source types, if the source span that you set doesn't extend the entire span of the simulation region, the source span will be automatically extended to fill the full width of the simulation region. This means that if you want to simulate a diffracting plane wave as though the plane wave is diffracting through an aperture of a specific size, the diffracting plane wave type must be used. Finally, the BFAST method should be used to simulate broadband angle injection when the light is injected at a fixed angle over all wavelengths. And for more details about the BFAST method, see the links below this video.